Okay, so let's start with Q meters. Okay, so basically Q meters or quality factor meters. These are used to measure quality factor of a coil as well as the R, L, and C of an electronic circuit, especially at radio frequency, right? And since they are being used for measuring R, L, and C, so it is also called RLC meter. So generally, this Q factor meter or Q meters, these are an important thing to talk about, and this is what we will cover, right? So Q meters or quality factor meters, right? And since they are used to measure R, L, and C of an electronic circuit, it is also called as RLC meter, right? So Q meters or quality factor meters, uh, they measure quality factor of a coil at radio frequency, right? So this is one thing. So from here we start for Q meters. So in general, what oscillations are? If there is an L and C connected together in parallel, right? So one will provide energy. So this goes down. I mean, the energy of the inductor is transferred to capacitor. Capacitor is fully charged. Then it starts behaving as a battery and pushes the energy back and saves it into the inductor. Now the thing is, when there is a lossless combination, means L and C don't have any resistance, then in that case, these oscillations will continue forever, right? So this is about LC circuit and oscillations. Okay. So what we saw was that Q meters are typically used to measure the quality factor of coils at radio frequencies. Okay, then this also Q parameter also is used to identify or is also called as storage factor Q, right? So Q is also is known as quality factor as well as it is also known as storage factor. And what is storage? So this storage factor is power dissipated divided by power stored in the in that particular element, right? And it is generally, and by default it is defined as Q is equal to omega naught L by R. Omega naught is the resonance frequency and R is the effective resistance, right? Effective resistance is the resistance which is predominant at the frequency of interest, at the radio frequency of interest, right? Uh, in fact, this is also known as figure of merit of a coil. So, storage factor is also known as figure of merit of a coil. Okay. So in general, if I talk about a series RLC circuit, then what we have is we have R and L. We have R and L in series with a capacitance C. So what happens is we define, and this RLC circuit is powered by a radio frequency oscillator, right? So this is a power source which is supplying an electric voltage of E, right? So this is supplying the power and is powering up this, and because of this, some current I naught at resonance frequency flows, right? Through or flows through all these three elements. Fine. So as we can see, this I naught is flowing. So this I naught is the same through R, L, and C. So whatever is flowing through the R can be shown like this in phase, right? And when this current enters into inductance, the voltage generated across the inductor, let me show it as capital EL, right? Because here it is, I have written it as capital EL, so okay, let it be. So this voltage will, so rather this current will be leading by 90 degree. So rather, sorry, this is voltage, है ना? We are talking about voltages and we are plotting the voltages, and voltages are being measured by this, right? So the voltage, and actually this is a phasor diagram, which is voltage current relationship, right? So voltage current relationship. So the voltage drop will be in phase with the current flowing through the resistance, whereas the voltage across the inductor, shown as capital EL, will be leading by 90 degree with respect to the current, and whatever what the value of this will be I naught XL, right? And since E subscript L is showing the voltage drop across R, L, and together, and therefore we have this EL, which is the vector sum of the voltages across R and L together, will be shown as EL, right? So E subscript L is the effective voltage, whereas when I talk about the voltage across the capacitor, this will be I naught XC, right? So this is I naught XC, and since this is a capacitor, this voltage will be lagging behind the voltage across the resistance, and therefore this will go down and the magnitude will be I naught XC. So this is EC, this is EL, E capital L, and this is the effective, the actual voltage across the resistance E. So this is known as the phasor diagram of series RLC circuit. Fine. Now, when we go further, now at that particular resonance frequency, omega naught or 2 pi f naught, right? So the XC will be identically equal to XC. So the resonance at resonance, the imaginary part will go off, and therefore XL is equal to XC. So this is XL and this is XC. So omega naught L is equal to 1 by omega naught C. So I can write omega naught square is 1 by LC, and therefore 2 pi f naught is equal to 1 by square root of LC, and therefore F naught is 1 by 2 pi square root LC. Right. So this is the resonant frequency of this typical RLC circuit. Okay, of the LC circuit. Then what is the I naught? I naught is the E by R, right? So this is how this can be calculated. Fine. So now you see What is EC? EC is I naught XC, which is at resonance equal to EL is equal to I naught XL, and therefore EC is equal to I naught omega naught L, right? Because EC was equal to I naught XC, XC is equal to XL, so I can replace XC by XL and write its full form. So I naught XL is equal to EC, voltage drop generated across the capacitor, right? And therefore, EC is equal to I naught omega naught L, and E is equal to I naught R, right? And therefore, I can now generate a ratio. So EC by E is equal to omega naught L by R. I naught will go off, and therefore omega naught L by R has been defined as Q factor, and therefore what we know is EC is equal to Q times applied voltage E, right? So I can even call this to be as amplification factor, and therefore in a circuit like this, now you can see we have applied a voltage E. We varied this capacitor value, Young capacitor value, such that it reached to its highest value at resonance, because a highest voltage generated across the capacitor will be occurring only when it is resonance frequency. So at resonance frequency XC, so EC is the voltage appearing across the capacitor, right? Is the voltage appearing across the capacitor, and this is the, I can call it as output voltage. So output voltage by input voltage is equal to the quality factor. EC by E is equal to Q, which means output voltage is equal to quality factor times input voltage, right? So this is what we have seen now. So in a practical circuit, what happens? We have the terminal T1, T2, across which we will place a unknown or the coil of interest, which we want to of which we want to measure the quality factor, and it is connected in series with a variable capacitor C, right? And this whole circuit is powered by a radio frequency oscillator, right, which has certain internal resistance, and then we place one R shunt resistance or series resistance over here, so that this radio frequency current goes into, and through I square R, there is a power dissipation, as well as in this power dissipation we have the voltage drop generate across this R shunt, right? Generally the value is in the range of even 0.02 ohms, 0.02 ohms to 0.2 ohms. It is much less, and whatever is this voltage generated or applied across this R shunt, there will be heat dissipation, right? And a voltage drop will be generated. Now this voltage drop is applied on this electronic circuit, RLC circuit, where C is a variable. So now what will happen? We will start varying this capacitor value, right? We will vary this capacitor value and accordingly find resonance at omega naught. So EC, this EC will be maximized So at that point of time, whatever is EC divided by E input voltage, right, will be equal to or give you the quality factor, right? Now, since this resistance applied is very small and we want to measure how much is the uh, radio frequency, the power applied at radio frequency, uh, it is measured by using thermocouple voltmeter, right? Thermocouple voltmeter is what? Thermocouple voltmeter is a very high sensitivity thermocouple based voltmeter. So here I have shown the thermocouple uh, voltmeter. So this is a nickel chromium bimetallic strip, right? A thermocouple. Uh, at one terminal we have since radio frequency RF signal is applied, this will generate heat. Because of this, there will be some temperature, right? At this junction the temperature is T1, at this junction the temperature is T2, the other junction, right? And therefore there is a temperature difference. So E induced is now measured through electronic voltmeter, because otherwise measuring this resistance, the voltage drop will be very difficult. So we have found out or used a thermocouple voltmeter which will generate EMF, and this EMF is electronically measured, so which is actually equal to the applied voltage, right? So E induced is proportional to constant A into T1 minus T2 plus constant B, T1 minus T2 square, right? So there is some proportionality constant, so you can check it in the book, right? So E is equal to K1 times this much, where generally the value of A is 40 to 50 microvolts per degree centigrade, whereas the B is considered to be in the range of 10 to 100 microvolts per centimeter, per degree centigrade square, right? And this component this component is much greater than this component, and therefore only this much is considered and used, right? And accordingly finally we can find the E induced is equal to the proportional to the whatever current is actually flowing, the square of the current. Okay, so this is how this is practically measured. Now, once we have done that, now we go further. So now you see in this circuit here, you can see that we have RL and since this is a lossy coil, it will have some internal resistance as well as its own inductance, and there will appear some distributed capacitance, right? So that is CD is distributed capacitance. Similarly, over here in this circuit, in this whole circuit, what we see is that the actual effective resistance has been supposed to be capital R only, whereas actually R is not that much. In fact, there is R shunt resistance applied, right? Uh, so effective actual the true resistance will be R plus RSH. So technically speaking, the so effectively, technically speaking, Q measured is equal to omega naught L by it should be R plus RSH, right? Rather than only using R. If I generate the reciprocal, 1 by Q measured is equal to R plus RSH by omega naught L. Similarly, Q true जो है, वो तो actually this will be equal to omega naught L by R, which is by definition, right? So if I obtain the ratio of these two, right? So Q true divided by Q measured is equal to 1 plus RSH by R. Fine. And therefore Q true is equal to Q measured multiplied by 1 plus RSH by R. Now, if RSH is much smaller than capital R, naturally, you will be able to measure, the measured value will be equal to or very close to true value, right? So this is one correction generally made while measuring Q parameter. ठीक है, Q factor के लिए. So here we have considered the distributed capacitance. Now, so this is what we have checked. So when you will check it further, you will find it like this. And correction induced distribute because of the distributed capacitance. अभी हमने क्या किया था in this the previous slide, in this current slide which I am showing now is was considered about this R and RSH. So it was because of the shunt resistance. Now what is the difference or change that occurs due to the capacitance? So you see, this distributed capacitance will get in series with this gang capacitor, and therefore the actual effective capacitance will be C plus CD. Okay, so I mean this is the series combination of this. Okay. All right. So when you will go through the book, you will find that it is a Q true is equal to Q measured bracket 1 plus CD by C, right? So similarly, if we measure inductance, you can just go through the theory. I mean, we have already derived earlier, na? What we had derived, F naught is equal to 1 by 2 pi square root of LC. So if you know the resonant frequency and the capacitor value, you can also measure the inductance value, right? Similarly, if you know omega naught L and Q true, then effective resistance of the coil or the circuit can also be measured. So in this way, we are measuring over here L, over here we are measuring R. If other parameters are known, we can measure C, right? So in this way, there are ways by using which we can measure the capacitance also, RLC. So how much is the distributed capacitance? So we will use two frequencies, right? One is F1, one is F2. So at frequency F1, right, what we will get? The capacitance is a particular capacitance C1, so C1 plus CD. So at frequency F1, the equation will be like 1 by 2 pi square root of L within bracket C1 plus C2. The other frequency which we have chosen F2 is twice of F1, right? So under this condition, the effective capacitance will be C2, right? The resonance will be obtained at C2. So this, in this case for F2, this will be 1 by 2 pi square root L within bracket C2 plus CD, right? And therefore, since there is a typical relation between that, this is F2 is equal to twice of F1. So using this relation, now I can place it like this, and I can solve these equation and finally to find that CD is equal to C1 minus 4C2 divided by 3, right? You can also solve it, derive it, and make sure that you are able to derive and show it if it comes in the examination, right? So one has to be very careful about the derivations as well. Acha, regarding the bandwidth, what happens? Regarding the measure bandwidth, okay, how to measure the bandwidth? So we have the center frequency as omega naught. Now I want to know how much is the bandwidth of my circuit. So bandwidth is defined as the half power frequency, and at that half power frequency, the effective voltage VF1 will be equal to V naught by square root 2, and similarly the current will also be 1 by root 2. So that is known as half power frequency, the bandwidth. And by definition, bandwidth of a circuit is equal to the frequency range at which the power output power reduces by half. So if input power is P at resonance frequency omega naught or F naught, then if I keep on increasing the frequency beyond F naught, gradually because of the higher frequency, the output power will start decreasing, and the frequency at which the power decreases to half of the highest power, right, is the higher the cutoff frequency. Similarly, you start reducing the frequency and maintaining the input the power same, but your output power will also come down when the frequency comes down to F1, and therefore F1, F naught, and F2. These are the three frequencies. So F1 minus F2 is the bandwidth. So this is how. So even quality factor is defined like this as well. Q is equal to omega naught by omega 1 minus omega 2, or F naught F0 by F1 minus F2. So this is also a quality factor. Okay, so this is how measurement of bandwidth is also done using a Q meter, right? So how to measure an unknown capacitance? So we should be able to do that. Okay. Now there are succeeding slides which I took from certain PPTs, right? So these are the same reiteration of the same things. There are some numericals you can just go through, which will be helpful, and sometimes such questions may also come. Now the things are explained better, so maybe for the understanding purposes, you can go through this structured content also. Previously, I have explained what it was, right? So please go through the book, check for the details, and then, okay, this is fine. This will help us immensely. So make sure that you have gone through various questions. There are some books which are already uploaded on the Teams folder. So please go through respective chapter. For example, this is the Sahni, the book by A.K. Sahni, chapter 23. So there you will find some questions on Q meter. Similarly, other books are also there. So please make sure to go through the questions and understand them well, right? So, okay, thank you so much for this patience, this much patience. I believe it might be some 45-minute content. So please go through, and Q meters are very important from the understanding point of view. Okay, so good luck for good understanding. Please have a good time. Bye.